Hello, we've seen the ray diagram of a transmission electron microscope and we've drawn comparisons with an optical microscope. Right now, we are next to the JEOL JEM 2100, which is a lanthanum hexaboride filament operated TEM. This microscope runs at 200 kilo electron volts, and here are the various components of the microscope. As it was discussed or informed a little earlier, this portion is where you have the electron gun. In this case, in this instrument, we have actually a thermal emitter. It's called as a thermionic emitter. And then in this portion, you have the condenser lens, and over here you have the objective lens. So in this microscope, you have a side entry holder, and over here you have a split pole piece type objective lens. What you see here is the condenser aperture. Here is a hard X-ray or a shielding aperture, and this is your objective aperture. If you go a little down, all over here is where you have your projection lenses. When you start imaging, you start by aligning the microscope by starting with each of these individual components in this particular sequence. It is not a hard and a fast rule that you always stick to the sequence, but it is a healthy practice and it is easy to remember if you start by aligning your emission system, condenser aperture, and then you load a specimen over here, you adjust the specimen height, and then you start imaging. Once you start imaging, you record the data over here. You see the data on the fluorescent screen as you see here. And if you go further down, there's a camera below. And on this microscope, we have a CCD camera on which you record the digital images. In the old school microscopes, you actually had photographic plates and you were exposing the electron beam and opening a shutter and recording the images on a photographic plate. So this is general layout of a transmission electron microscope. Now, if I move behind the instrument, so we'll look at general layout of how a transmission electron microscope is laid over in laboratories in general. What you have is the main instrument column here. You have the high tension tank behind the microscope here. So the high tension tank is essentially acting like a step-up transformer where you're withdrawing power from the main line either at 100 or 230 volts, and then it runs through a loop over there, and you have the high tension tank acting as a step-up transformer. So here is the cable which is connected to the microscope column here near the source on the top, and the electrons are accelerated through 200 kilovolts in this particular column here. If you come a little closer, what you see here is the oil diffusion pump at this portion, and right here it is connected to, in this particular instrument manufacturer, you call it as a sputter ion pump. This has a 200 liter sputter ion pump, or the other manufacturer calls it as the ion getter pump. The vacuum system of the microscope, as informed, it runs under ultra high vacuum, and to obtain basic vacuum all through, you have a few roughing pumps in the background here. So the roughing pump is connected to the oil diffusion pump. In some cases, you may have a turbomolecular pump, and once you achieve about 10 to the minus 3 or 10 to the minus 4 millibar, your oil diffusion pump starts on, and once you steadily achieve a vacuum of around 10 to minus 5 millibar, that is when your sputter ion pump takes over, and that is how you achieve ultra high vacuum in a microscope column. We'll move gradually to the other side where the electric console is. So here's your electric console, and typically once you come to the microscope, a good practice is to check if this LED is on, if you are using a JEOL instrument. So you can just look out what the current reading here is for the sputter ion pump. This gives an indication that your ultra high vacuum, especially the vacuum reading on the sputter ion pump, is at a good value. And once you check that all this is ready, you can start by loading a sample and inserting the holder into the microscope. Now, if this is not ready, what you need to check is there are various reasons what could be wrong. One could be a simple shutdown of the lens. It could be a lack of supply of chilled water, or it could be any other reason. It could be a previous user not removing the holder properly. So we'll look at the software interface and then see what could be the reasons why an instrument might be off. But if these lights are on and all the readings on your screen are okay, you are in principle ready to go and insert a holder into the microscope. We'll quickly have a look at a few more details here. So this is your roughing pump. There's a little lead block in which the vibrations are damped, and the power console and the tubes here are to supply or circulate chilled water into the microscope column. So if you look at a chiller, this is how a typical chiller connected to an electron microscope, a TEM, looks like. You can see the readings here. It just gives you the temperature of the water that is being circulated in the microscope column. Remember, when you're using electromagnetic lenses, they often get heated up, and to maintain the lens uniform at a given temperature, you're circulating chilled water. If you come in closer, so here's the chilled water that is being pumped in. It is typically deionized water, and as long as this is circulating, you do not have an issue with the chiller. Sometimes it so happens that you have an error on the chiller, and this could be one of the reasons why your microscope stops. Yeah. So as you've seen, the general layout of any transmission electron microscope is you withdraw the power from the main line, which is either 230 volts or 110 volts, depending on where you are. And from there, if required, this instrument being from a Japanese manufacturer, we have a step-down transformer. And with the power situation in India, we generally have an uninterrupted power supply. So the raw power goes through our UPS and then to the step-down transformer. And from the step-down transformer, we power on the electric console. And once you check that everything is in order with regard to the power and the vacuum and so on, you are good to go and start loading a holder into the microscope. So when I talk about a very thin electron transparent specimen, it is very difficult to handle these specimens. Typically, you can put these specimens on a 3 millimeter grid, which looks like this. So here is a copper mesh on which you have a thin formwer or carbon layer on top of which you can deposit nanoparticles. And next to this is a standard 3 millimeter electropolished specimen or even ion milled specimen, which appears like this. So you introduce these into the microscope column by using a specimen holder. So what you have here is a standard single tilt specimen holder for the JEOL microscope. You have an equivalent version for Thermo Fisher microscopes as well. So the idea is there is a very small slot here, and in this hole that you see, you load this 3 millimeter disc or 3 millimeter grid, and then this goes into the microscope column. When you see, this is called as a single tilt holder because this holder has only one axis of rotation, which is along the axis of the holder. And the other kind of a holder that we typically use is the following. So here is a standard double tilt holder. The idea is you have a small motor inside which applies the secondary tilt. So the primary tilt or the first tilt, like the previous holder, is along the axis of the holder. And when I do the double tilt, this actually goes into the cradle here. When I do the secondary tilt, the cradle that you see here is actually tilted. Connect this to the goniometer here and then see how the tilt happens. So this is the double tilt holder. So the primary tilt is along the axis of the microscope, which is like this. And the secondary tilt or the beta tilt or Y tilt as it is called is where this cradle moves up and down. As you can see, the tilt is restricted within plus minus 15 degrees for the secondary tilt and about 30 degrees for the primary tilt for a typical microscope. Depending on the type of analysis you do, you either use 3 millimeter discs with carbon mesh, or you prepare specimens by ion milling or electropolishing. For a nanoparticle sample, for a powdered sample, it is always a practice to use a holy carbon grid or a lacy carbon grid or a continuous carbon grid. So the grid is inserted into the specimen holder like this, and very carefully you close the holder. And most of the times for nanoparticles and powder samples, it is okay to do with a single tilt holder. But when I want to do some kind of diffraction study and get some meaningful electron diffraction analysis, I usually use the double tilt holder. So what I'll do is gently, I'll close these screws and close the lid of this. And bear in mind, always put your gloves on. This portion which goes into the microscope column should be absolutely clean, and the specimen rod in general also has to be clean. And while you're applying a torque on the screw, I generally do not recommend using the index finger, but because you can end up applying too much torque. So place your finger on the top and then gently just do it finger tight, just to be sure that you do not damage any of the sensitive parts in the holder. And then another practice which we usually have is, after you load the specimen into the holder, it is generally a good practice to give a gentle tap and check if the specimen is sitting properly. Once this is done, you also check if there is any contamination near the O-ring, which is over here. Usually, when the holder is lying outside for very long, it is possible that you collect some dirt particles, and any dirt on the O-ring will also interfere with achieving a good vacuum in the microscope column. So once your O-rings are clean, your specimen is loaded, you can load this into the microscope. So I'm interested in loading a sample in the double tilt holder. As you can see, this is the double tilt holder. On a JEOL microscope, you insert the holder this way, you position it aligned with the sort of keyhole which is shown here, and the little screw which is on the holder has to go along with this direction. So your cradle stays vertical and it goes in carefully. Please be sure that you're not touching any of the tube inside, and it goes in. Once you go there, you just hold it with your finger and you wait to hear a click sound, and you hear those two clicking sounds, and then you can start pumping. So initially when I start pumping, the amber light goes on, and you wait till the green light starts glowing here. Once the green LED goes on, then I insert the holder by turning this clockwise. So in the meantime, I connect this secondary tilt holder cable here, and I choose the appropriate holder in the software. When I once put the holder in and I switch to the pump here, after hearing two clicking sounds, the amber LED goes on, and I have to wait till the green LED goes on. Once the green LED is on, then I can turn the holder clockwise and insert the holder into the column. And after I connect this cable, I have to choose the appropriate specimen holder in the software. I have to ensure that all the readings in the software here are showing as evac ready, and you're ready to insert the holder. And once I insert the holder, I switch on the switch from air to pump. Now once the green LED is on, as you see here, I have to carefully turn the holder by gently holding this, and it goes in by approximately, on a 15-degree rotation, it goes a step in. And now I carefully turn it by 75 degrees more clockwise, and I should hold this holder such that it does not crash into my microscope column. So once the holder is in, you are good to go with imaging. When you come to the microscope, and if you notice that none of the software is on, for this particular JEOL instrument, you have to see that the TEM server is on. You get an indication here on the bottom right corner that the TEM server is on. And then you switch on the software here, TEMCon, which is the TEM control software, and you see multiple status windows here. And when you go to the other PC which has the control for the camera software, you switch on the camera software depending on whichever manufacturer camera you're using. And what you see here is mainly the following. you should see that the high tension is on. It is in green here. And if the holder is inserted properly, you see this indication that beam is ready. If I click on HT page, I get this window. If I click on more here, I get the status of what the extraction limits and what the emission limits are and how to switch between different high tension values. If I look at the vacuum page, I get an idea on the layout of the vacuum system of the microscope. Some time ago, we saw that there were roughing pumps and there were several other kind of pumps, which is the oil diffusion pump. You had a rotary pump, and then you have the sputter ion pump here. On this instrument, it's a 200 liter sputter ion pump. And as you can see, the sputter ion pump is connected between the column around the specimen area of the microscope. Now, once the holder is in and everything is ready, you see the status that evac ready is shown on all these here. Typically, these current values are mostly less than 30 microampere. If it is beyond 30 microampere, then your vacuum levels are slightly high on this instrument. And the RT or the PIG5 value is showing evac ready, so you're not too concerned about this as long as it shows as evac ready. And one of the indications is you see this green light here in this bar, and on the electric console that I spoke about a little while ago, the SIP should be on, showing it in green color. So once the holder is loaded, what I do is I come to the interface here. I have two control panels, two control consoles, and I have one joystick here. The joystick or the trackball here is for moving the stage. So the specimen holder is moving in the XY plane when I move this. And there's a piezo control and there's a knob for coarse and fine movement. If I focus on the control panel on the left, I see various details. Now, like I was mentioning to you, the first step of alignments, I start by checking if my probe and my illumination system is proper. So all those knobs are over here. Some of them are on the left and some of them are on the right. On this location here, you see the probe control. So you can switch between the TEM mode, the EDS mode, the nano beam diffraction mode, or if you're doing convergent beam electron diffraction. There is aperture control here. On this particular microscope, we do not have motorized apertures. But if you have motorized apertures, you can in principle control the apertures by selecting these. Now, what you have here is a sort of a normalized thing. If I press this neutral, it runs through a loop and resets all the currents of all the lenses and all the deflector coils to the default value, which is close to the alignment value. I can choose the alpha, which is setting the convergence angle for my illumination. Typically for bright field TEM mode, I have a parallel beam illumination. The spot size is to choose the brightness of the electron beam that is incident on the sample. It is counterintuitive. If I use spot size 5, that is a higher number, the beam current is actually smaller, and spot size 1, the beam current is actually higher. Also, the beam diameter is larger in spot size 1. The default values vary from instrument to instrument, but typically you can discuss with your facility manager and with the manufacturer to get a clear idea on what the diameters are and the convergence angles are. Now, the other important knobs here are you have the deflector or stigmation knobs. You can use the knobs. So most important thing is, if you notice, I have to move from the left console onto the right console as well. I have two shift knobs, one on the left console and one on the right console. And I have two deflection or stigmator knobs on the left and right console. Now, on a Thermo Fisher microscope, instead of having these shift X and shift Y knobs, you have a trackball. And on a JEOL microscope, you have these knobs. And on a Thermo Fisher microscope, you call these deflection or stigmation knobs as multifunction knobs. And here you have this def/stig knobs. I can choose I can choose the step in which I'm causing a shift by pressing this coarse button. So as you can see, the LED backlight goes on here. This means I can shift in bigger steps when this is selected. Likewise, the same applies for the deflection or stigmation knobs. The brightness knob here, or the intensity knob as it is written on the Thermo Fisher microscopes, is changing your strength of the condenser lens. So what you're doing is, when I spread the beam or when I converge the beam, I'm controlling it by playing with this brightness knob. So that is about what you have here on this console. Most importantly, by selecting one of these buttons, I can activate this deflection or stigmator knobs. I can cause image shift by actually changing the coil strengths there, by changing one of the values on the illumination lenses. And instead of physically moving the sample, I can virtually move the image when I select the image shift law. There is something called as the PLA. This is typically used to shift your diffraction pattern. And you have the condenser stigmator and objective stigmator. When I start showing you the alignment procedures, I'll talk to you in more detail on how to choose and when to correct the condenser astigmatism or the objective astigmatism. Likewise, depending on the mode in which I'm imaging, I either have the dark tilt or the bright tilt knob. This comes in handy when I'm doing a weak beam imaging, or when I'm doing, for example, a two beam condition, or to do dark field imaging. If I now switch to the right, this section here is only useful if you have a plate camera and to record photographs on a negative. What we have is, in this portion, the Z plus or the Z minus button. So with this, I move the height of the specimen stage upward or downward. This comes in handy when I'm correcting the eccentric height. And here I have something called as the image wobble X and image wobble Y, and I have the HT wobble. So what these image wobble X and image wobble Y do is the following. So when I select the image wobble X, you can see that the condenser 1X and the image 1Y values are changing slightly. And when I switch to image wobble Y, it does the condenser Y and condenser 2X and the image lens here. So what you're doing, and when I do the HT wobble, it changes the image lens 1 voltage slightly. So what is happening here is, instead of physically moving a specimen, with the wobble functions, I'm slightly changing the voltage of the illumination lens such that my image moves slightly. I will show this in a little more detail when I come to the alignment of the eccentric height. You also have these function knobs here. Different instruments and different locations, different labs have different conventions. Over here, the shortcuts to what these function knobs are given here. For example, when I press F1, it is the screen lift button. The F2 is if you're using an off-axis camera, F3 is to change the spot size, and F4 is for gun alignment in this particular system. Nonetheless, depending on which facility you're using, these function knobs might have different assignment. And if you come closer here, you have the magnification knobs here. You have different modes in which you can operate the microscope. You have the mag mode, the low mag mode, the SA mag mode, or the SA diff mode. So I can show the schematics of what is changing between these different modes. But typically, when I'm operating between a magnification range of around 8,000 to 200,000x, I usually use the SA mag mode. And when I'm going for higher ranges of magnification between 200,000 to even 1 million, I use the mag 1 or mag 2. Both of them mean the same. This is essentially two different memories to save your previously used magnification. If I switch to low mag mode, this is also similar to the Lorentz mode. What you're doing here is, this Lorentz mode is only in particular for the JEOL microscope. You can see that the lens voltage here of the objective lens goes off. For example, in SA mag, my lens is at 3.67 volt here, and when I switch to low mag, the objective lens goes off. In this condition, I can go anywhere from low mag 50x all the way to around 5000x. This is to search for a transparent area within the sample. Next, I have the diffraction focus knob here. So when I'm actually switching to SA diffraction mode to obtain a diffraction pattern, I can use this to focus my diffraction spots. Then these two knobs are analogous to the shift X knobs that I had on the left console. These are the shift Y and deflection and stigmation Y. I typically use these two knobs on the left and right console together. I have the magnification knob here. So as you can see, if I switch from, when I turn the magnification knob, I can choose the field of view that I'm actually checking. Or if I'm in the diffraction mode, by changing the magnification knob, I change the camera length. Like I mentioned slightly a while ago, when I press this coarse button, the rate at which I change the focus is actually changing. And then to focus the objective lens, I have two separate knobs here. On the Thermo Fisher microscope, the objective lens and the diffraction lens are focused using the same knob, but on the JEOL microscopes, you have two separate knobs here. If I press coarse here, or if I remove coarse here, you can do fine adjustment or coarse adjustment of the focus. So this is the basic layout of your console. We will now start with switching on the electron beam, and we'll do basic alignment by adjusting the objective aperture here. Once I start imaging and I switch on the beam, I have to turn off the light, so it is not possible to show this. So focus, when I want to adjust the aperture, I adjust it either by moving this or by moving this. This is for the in plane and out of plane rotation of the aperture holder, and this is for displacing on the X direction. So it is like X and Y combination. This comes in handy when I want to insert an objective aperture, to choose a specific reflection, to correct my condenser astigmatism, or to correct my illumination and adjust the condenser aperture. I have to use these two knobs. And likewise, when I want to do selected area diffraction, I have to do the same with these knobs here. Okay? You have a cold trap here. This is called as an anti-contamination device here in a JEOL microscope. And you also use a Dewar in a Thermo Fisher microscope. What you do here is you fill in liquid nitrogen, typically around 1 liter. And this is like a cold trap, which is ensuring the vacuum of your sputter ion pump is maintained within 10-5 millibar or lower. This is extremely important and one of the first things you do when you come to the microscope. So to switch on the beam once the holder is inserted and all the vacuum values are ready, so I have to press this button here, and you'll notice that the illumination would start here. So as you can see, the extraction has started. This is a thermionic emitter, and it is shown in the percentages here. We've set a limit of about approximately 59.6%. So at some stage, the illumination should start. So on switching on the beam, you'll notice that you'll have some illumination on the screen here. So the first thing you'll do is you go to low magnification, as low as you can, and then you search for a transparent area within your specimen. Typically for electropolished samples or 3 millimeter discs, where you form a small hole by either electropolishing or ion milling, finding the hole is the first step. And once you're close to a hole, you know that the area to the adjacent of the hole is an electron transparent area. So for example, when I switched on the beam, I spread the beam like this. So I go to the SA mag mode on this instrument, and we find a sort of an electron transparent region. Now the first thing that we do is we bring the specimen to the right height. So I'll just search for a small area, and hopefully this is slightly more transparent than the other. In this configuration, as you are not at the eucentric height nor close to the right focus, the specimen appears more thicker than it actually is. But in reality, as I converge the beam, so if you look at the intensity knob, I'm squeezing the intensity knob, or I'm squeezing the electron beam by turning the intensity knob to the left or right. And this indicates your sample is not at the eucentric height. Now, if I use the same operation on a Thermo Fisher microscope, correcting the eucentric height, there is something called as the alpha wobbler. So where what it does is it tilts the specimen holder with an amplitude of 5 degrees or 10 degrees or so, and you see that this thing changes. But in the JEOL instrument, you either click on image wobble X or image wobble Y. One important step is you go to a magnification of somewhere between 25,000x to 40,000x. Identify a feature of interest. I'll just go to one of the edges of the sample here. So this is a metallic sample, it is an aluminum sample, and on this I am at a magnification of 40,000x in SA mode, and I click image wobble. Now as you can see here, I do not see anything, and it is like, because you are changing the lens voltages of the illumination lens that I showed you earlier, I do not see a steady image at the center. I can correct this by changing the height of the specimen. So before I do that, I have to click on standard focus here and then bring it to the center, and let me correct the height. So I'm moving downwards. It can be downwards or upwards. I don't know if I'm going in the right direction yet. I see some sort of features here, and so when I go in the upward direction, it was not coinciding. So what I want you to notice is, at the edge of the specimen, you see a kind of a brighter or a darker shadow. This is called as Fresnel fringes, and by letting all of them coincide, I come to the stage where the contrast is minimum. Now I'm converging the beam again, and if I check the image wobble now, you see the image does not move and it remains more or less at the same location. So what exactly is happening here at this condition is the tilt axis of the specimen holder, the X tilt axis or the alpha tilt axis, which is along the axis of the holder, is now coinciding with the optic axis of the microscope. Now when this happens, I'm doing an operation by pressing the pedals below here. Now tilting the specimen by a few degrees, and if you come back here, so even with a 3 to 4 degree tilt around the zero value is not moving my feature of interest away from the field of view. This is an extremely important step and a critical first step when you're imaging in the transmission electron microscope. You're correcting the eccentric height so that when you want to do any diffraction analysis or any further analysis, or even orienting the sample into the right crystallographic orientation for performing high resolution TEM analysis, ensuring that your specimen is at the eccentric height allows you to tilt the specimen without moving away the feature of interest from your field of view. Now, after I move the specimen to the right eccentric height, I go into the hole of the specimen. As you can see, I see some kind of a shadow from the edge. This is a metallic sample, and what you see there is basically a diffraction contrast from the grain. So if I move it away, I do not see anything here. Right now, no aperture is inserted, and you see this funny shape. When I converge the beam or when I spread the beam, at the crossover point, this is what you have. Now the first step is improving the quality of the beam that I am focusing to a point. Why is this important? If I use this kind of a beam and I obtain any diffraction pattern, in fact, it doesn't affect significantly for high resolution imaging because I usually spread the beam and I look at a very small area. But by using an aperture, I can now improve this. So I'm now putting in the first condenser aperture, which is about 150 micron on this microscope. So if I now converge the beam, what you notice is there is an oval sort of a shape. Here is my crossover point. Now I'm turning the knob to the left. I see the oval is changing with its minor axis towards the 10 o'clock direction here. And when I come to the crossover and when I turn this way, you see there is sort of a rotation of the minor axis. It is around 2 o'clock position now. Bear in mind, you might be looking at a recording which is at an angle. So in the video, it may not really appear circular. But the first step that I need to do is I have to ensure that my aperture is aligned. So what do I mean by aligning the aperture? So if you see, when I turn this way, the shadows of the edge of the first condenser aperture should coincide at one point. So I'll now use the Shift X and move this to the center. And here is my crossover point. I correct it by moving the X and Y on the aperture, X and Y knobs on the aperture, and you really do not know where the exact center or the point of coincidence is. You have to do it iteratively a couple of times if it is badly misaligned. So here is my crossover point. This shape change when I go around the crossover by turning the knob onto the left or right, this typically happens if you have condenser astigmatism, which is the next step of correction that we'll do. But the first step is, here the center point is more or less aligned. I can do it even more finer, but typically you will not improve significantly. Perhaps at this point, it is more or less corrected. How do I know that it is actually properly centered? Is in a lanthanum hexaboride filament system, I'm not sure if it is visible in the video very clearly. You see a shadow around the edge of the aperture, typically a slightly brighter line. This is more prominent in a FEG TEM system, but in a LaB6 you do not see the shadow very clearly. If I converge it closely, Maybe the shadow is slightly visible. I'll try to make the shadow as concentric with the edge of the aperture like this. This is a kind of a hint that it is more or less aligned. And I'll also correct the condenser stigmatism. Now, the condenser stigmatism is typically corrected beyond the magnifications of 100,000 x or more. So I'm going to say 150,000 x or 200,000 x, it doesn't matter. And I move this to the center. And what I should do is, I've been shifting the beam left and right by using the beam shift knobs, which is the knobs that are on the top here. And if I press condenser stigmatism here, I've shown the layout of the console earlier. After I press the condenser stigmatism, I have to use the deflection or stigmator knobs. Now, in a Thermo Fisher microscope, you would have this as stigmator, condenser stigmator in a window in the software, or you also have it on the console, and you'll enable the multifunction knobs there. Here you enable the deflection or stigmation knob and try to make this as circular as you can. Now, after I make it as circular as possible, on either side of the crossover, you see this little misalignment is again because the aperture is not perfectly centered. So what I'm trying to do is, I'll move this with the beam shift knob, and so the top left edge of this circle now is where the center or the crossover point is coinciding. I want that to be centered with the shadow of the aperture. So I'll move this now slightly left in the upward direction, and I'll see if the crossover is coinciding. Like I was mentioning, this is a lanthanum hexaboride system, so you would not have it properly circular and sharp as you see with the FEG system, but you can say this is a more or less so because this is slightly older filament and the coherency is not as good as a new lanthanum hexaboride filament, you'd be mostly spending a lot of time trying to correct this, but it won't go beyond this on a lanthanum hexaboride system. So I would say this is sort of corrected. So if I use a larger amplitude for the intensity knob now, or a larger step size, I see that on the either side of the crossover, it is more or less coincident at the same point. This condition, my aperture is aligned, and I've also shown you that the condenser stigmatism is sort of corrected. Now, I go to the region of interest, to the edge of my specimen, and I start seeing the features here. So as you can see, there is some region here. So when I say a bright field image, there is nothing in the path of my microscope, in the path of my electron beam rather than the specimen, and I have a bright background and the specimen features appear darker. So I've not inserted any objective aperture, I've only put in the first condenser aperture, and I can obtain an image. So I'll just lift the camera and then show you on the screen how this image looks like. So the feature of my interest, I want to move it to the center. Typically on the microscope, you also have this small screen which will come up. So I can use this to align the feature of my interest onto the center. And if I now lift the screen, this will more or less be centered with the sensor or the camera that you're using. Please note that there are some markings here. On a Thermo Fisher system, you'll see some circular inner ring and then concentric circles. And on the JEOL system, you see these kind of square edges or rectangle corners. So if I lift the screen now, I'll take your attention onto the computer screen here. The feature of interest is on my screen. Bear in mind that your CCD cameras can be very sensitive. You ensure that you fill the screen completely, spread the beam completely, and your exposure time is not very high. Typically a 200 or a 500 millisecond exposure is safe for any cameras. In some cases, you might also use up to 1 second exposure, depending on the kind of cameras you're having. And your feature of interest is here at the center. I can just record an image now. Now, this is how you obtain a very simple bright field image.